Here we go. All right, so sine inverse of a half. First off, let's talk about, that's what that -1 means. It means inverse, this little -1 power right there. That means inverse function. Now, what is an inverse function? Let's get that idea straight before we specifically go into sine inverse, cosine inverse, etc. An inverse function is one in which inputs and outputs switch. I don't know if you remember that or seen that in your algebra classes. Inverse function switches inputs and outputs. So let me make it real for you. I think that helps. So what if you have think about a toaster. What do you put into a toaster? You put in bread. So it's like I'm doing like a function, right? That's like f of bread, f of x kind of thing. That's all these are functions. And what comes, you put in bread, and what comes out? Toast. Or you put in frozen waffles, and you get out toasted waffles, etc., etc. All right, you get the idea. So that's a toaster. So a toaster is a function. It's a real simple example of a function. You put stuff in, you get stuff out. You put in bread, you get out toast. So with that in mind, let's think about what an inverse, that -1 means inverse, swapping. What would an inverse toaster be? What would you put in? Toast. Put in toast. And you would get out bread. It would just, that'd be very useful, wouldn't it? I'm just kidding. That would be dumb. But anyway, that would be an inverse toaster. Getting the idea, though. So it swaps, it switches inputs and outputs. Okay, so with that in mind, for a normal trig function, sine, cosine, tangent, any of them, what do we put in? Well, we put in angles, like 30 degrees, 90 degrees, or pi over 6, radians or degrees, an angle, an amount of opening. You know what I mean by an angle, right? It's an amount of opening between two lines. That's what I can say. The door, but I probably should close the door for quietness. But it's a perfect analogy. So the door is open 90 degrees right now. It's closing down, right? It's an angle. So you put in an angle, an amount of opening, in degrees or radians, doesn't matter, and you get out an answer, right? Like the sine of 30 degrees, like, for example, the sine of 30 degrees. What's the sine of 30 degrees? So can you guys picture the unit circle in your head? And the 30 degrees is right there. I'm hoping this gets more and more comfortable for you. So you picture 30 degrees is right there, right? 45 is the middle. 60's here. And then to do sine and cosine, remember it's over and up. Over the large amount, so that'd be root 3 over 2, up the small amount of half. Remember the 1, 2, 3? And which one is cosine and sine? Cosine is always the x, sine is always the y. Sine is always the heights. Are you getting comfortable with that? So sine of 30 degrees is a half, huh? So it's a half. So in other words, you put in an angle, you get out an answer, huh? For a normal sine, cosine, tangent, whatever. Now, so with that in mind, let's think vice versa. Let's think about an inverse trig function. So for an inverse trig, like this, sine inverse, you put in an answer, don't you? And what are we going to get out? An angle. Some kind of an angle. You get the idea? So for an inverse trig, sine inverse, tangent inverse, whatever, you put in the answer, get out the angle. You're swapping the normal, and normally sine you put an angle, get out an answer, inverse sine, vice versa. So what's the angle going to be? What angle has a sine whose answer is a half? 30 degrees. We just did it, huh? 30 degrees. Now, how would you find that on the unit circle? Let's go. So mainly what I would suggest use is the unit circle. So when somebody asks you sine inverse of a half, which I know we just did, but let's redo it looking at the unit circle. You would look at that unit circle and you go, okay, where is the sine going to be a half? Remember how this works. The x is always the cosine, the y is the sine. Cosine, sine, cosine, sine, cosine, sine, etc. all the way around, right? So where do you see the answer? Because remember, that's the answer in an inverse trig function, right? Where do you see the answer to sine being a half? Right there, 30 degrees. And there's another one, huh? Where's the other one? 150. Good job. 150 right there. Cosine, sine. You see, if you keep going all the way around, none of the other ones will work. But Chanel. Am I saying it right? Chanel. Sorry, I should know your name. well by now. Chanel. Yes. So yeah, Chanel's right on the money. 150 and 30 both have a sine of a half. No other values do, huh? There's two places where sine is a half. So which answer is right? Do we give the 30 degree or do we give the 150? Well, here's where, because they only wanted one answer to this kind of question, you might hear the way I'm talking, because they only wanted. Sounds like they're just making this up. They are. They are. I'm saying it exactly as it is. They made this because, remember, all of math is made up. Just totally made up to do things in real life that are helpful, right? So they made this up in a way that was helpful, and they said, we don't want two answers. We don't want two answers. So here's what we're going to do. When you do inverse sine, we're going to say only give us answers in these two quadrants. I'll write that out more in detail later. For now, let me keep it simple. I'll give more detail in a minute. They're going to say we're only going to go from here to here. We don't want any answers in the, second and third quadrants. Only these two quadrants. That's all. Because that way they only get one answer. They don't want two. So that's why the answer is only the 30 degree, not the 150. So 30 degrees. They probably want it in radians. They do. Yeah, so pi over 6, right? It's right with the unit circle. It's great. It's right there for you. Don't have to mess around or convert. Pi over 6, that's the answer to that one. Good so far? So it's, I overdid it there. It's more of negative a half. All right, so go to the unit circle. Let me put it here for us. In fact, why don't I just put it on the unit circle? Here we are. So we're trying to find on number 2, sine inverse of negative a half. Okay, so this is question number 2, sine inverse of negative a half. So you're gonna look around and find the place, and you're only looking in these two quadrants, right? That's by definition. They just made it that way, so we'd only have one answer. So if you're only looking here and here, where is the sine inverse negative a half? So remember, it's cosine sine, cosine sine, cosine sine, cosine sine, cosine sine, cosine. There it is. I don't know if you can see the negative. That's the only thing I don't like about this. They made the negatives too small. Negative a half right there. That's where the sine is named. So what angle is that? 330 or 11 pi over 6 in radians. If you type in 11 pi over 6, it'll go eh. Right. Yeah, you seeing that? I could tell Chanel you were on there. You're like, this isn't working, Mr. Hearn. Yeah, that is the right answer, but they don't want you to say it that way. They're being really picky. You have to say it as a negative angle. That's the other really picky thing about this. They have a real specific way they want you to say it. That is the spot. I mean, this is the total spot. But they want you to say it as a negative angle, right? Because it can also be said, whoops, fall over here, from 0 down, right? That's a negative angle. How much is that as, instead of saying, hey, it's all the way around 330 or 11 pi over 6, how about as a negative? That's what they want. So how much is that as a negative angle? It's negative pi over 6. Everybody see that? Because 11 pi over 6 is just 1 pi over 6 shy of 12 pi over 6, 2 pi. That's just 1 pi over 6 down. Negative pi over 6. Is that okay? Or you could say negative 30, huh? Because it's down 30, and that's pi is 180 over 6, 30, negative 30, huh? Everybody see that? So an important lesson then is this. Well, in fact, let me just give you the overall game plan. For answers, well, that sounds funny. For sine inverse and let me just give you the whole game plan. Tangent inverse, the angles go from negative 90 to, yeah, I mean, that's true. But let me draw it on a unit circle. It'll be easier to see and remember. So from here to here, negative 90 to positive 90 for sine inverse and tangent inverse. And then for cosine inverse, it's actually these two quadrants. Cosine inverse, it's from 0 to 180. So you can put that in your 3x5 card. So yeah, so that's how they want you to do it. This is negative pi over 2, positive pi over 2, and this is pi. So that's how they want the answers given, like that. All right, so let's keep going then. Okay, so I'm on number 3, which is, there's not room here. It's cosine inverse of negative root 2 over 2. Question number 3. So question number 3 says, do the cosine inverse of negative root 2 over 2. So now for cosine inverse, we're only looking in these two quadrants, right? The top two. So where do we see, again, it's, cosine sine, 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 cosine sine. Where do we see cosine negative root 2 over 2? Right there. Right, so see how that one's negative root 2 over 2. Yeah, it is 225 also, but remember, we can't go down there. Right, it's only these top first and second quadrant for cosine inverse. Yeah, because 225 would have been another spot, huh? So we have to take the 135 or 3 pi over 4. So 3 pi over 4 is the answer on that one. 3 pi over 4. They want the radians. We good? Making sense? So far, so good? All right. Okay. So we go. So question number 4 says find the tangent. So we've done sine and cosine up to now, sine and cosine. Now they want the tangent inverse of root 3 over 3. Tangent's always a little more tricky because that involves sine and cosine, doesn't it? Remember, the tangent is sine over cosine. So when you're so let me just write that down. So you always want to keep that in the back of your mind whenever you're dealing with tangent. It's more complex. It's 2 trig functions divided, sine over cosine. Okay, so I'm looking at this root 3 over 3 thing. So you realize it's not so simple. I can't just look at the unit circle and immediately grab it. I'm going to have to think about a combo of things that will make it. How so? Well, root 3 over 3, how am I going to get a sine and a cosine that will somehow together become root 3 over 3? How's that going to work? Well, think about our values. Remember that the 3 numbers we have: half, root 2 over 2, and root 3 are the small, medium, large, right? Everything on that unit circle is just some kind of combination of those, or 1 and 0. Right? It's 1 and 0 and those 3. So how can you get root 3 over 3 out of this stuff? Well, first off, it's not the middle guy. Remember, he only goes with himself. The middles just go with the middles. They never mix with the small and the large. This is clearly not any root 2s. It's a root 3. It's got to involve this guy somehow, doesn't it? Because we're looking at a root 3. So it's got to involve that root 3 over 2. But it's also going to involve that guy. Both of them together. Basically, one of them is going to be in the top and the other in the bottom. How do you know which way? Well, if it was root 3 over 2 on the top over a half on the bottom, if it was, would it really become that? Well, let's try it out. How would you simplify that big mess, root 3 over 2 over a half? What would you do? Yeah, you'd grab the bottom and flip it up and multiply by 2 over 1, right? The dividing's upside down multiplying kind of thing. The 2's would cancel, and that would equal just plain old root 3, which is not that. That's root 3 over 3. So it wasn't that way. It must have been the other way. Let me do it over here. It must have been the half on the top and the root 3 over 2 on the bottom. Let's see it. Grab the denominator, flip it up. 2 over root 3. 2's cancel. Am I going too quick? So 1 over root 3. And then multiply top and bottom by root 3. And you get this. Everybody see it? See how that works? So in other words, this root 3 over 3 did come from a half over root 3 over 2. We can see that now, because if you grab this and flip it up, the 2's cancel. It's 1 over root 3, and then you know what to do with 1 over root 3, right? You just multiply top and bottom, because you never leave roots on the bottom, right? So you multiply top and bottom by root 3, and you get root 3 over plane 3, because 2 root 3's in the bottom make a plane 3, which is our thing. So that means it came from a half over root 3 over 2, didn't it? And what's the top always? Sine. What's the bottom always? Cosine. So the top, the sine, so we're looking somewhere. Now we can go look at the unit circle. We're looking for where is the sine a half and simultaneously the cosine root 3 over 2.
Pi over 6.
Right there at pi over 6. See how, remember, it's cosine sine. See, the sine is a half. The cosine is root 3 over 2. Right there at pi over 6. At pi over 6, remember, it's cosine sine, right? So cosine's root 3 over 2. That's the bottom. Cosine's on the bottom, right? Tangent is sine over cosine. Sine's a half, goes in the top. As we show, when you simplify that, it becomes what we have for tangent. That's where they must have gone. Pi over 6. So it's a little harder, isn't it? You got to think about sine and cosine coming together. So the answer is pi over 6. Pi over 6 is the angle that would make tangent become root 3 over 3. Because sine's a half on the top and cosine's root 3 over 2 on the bottom. Now, having said that, let me make it a little easier for you for tangent. Because I'll give you a lot of tangents, and there's a quicker shortcut way where you can kind of spot it quicker. Here's what you do. When you look, basically it's all about whether the root 3 is the unique mark. You're looking for that root 3, and you're going, oh, root 3, that's the special thing. So it's all about if the root 3 is on the top or the bottom. That's the issue. But it's a little more tricky than that, because when you see root 3 over 3, that really came from a root 3 originally on the bottom, didn't it? And then they multiplied top and bottom by root 3, and then it ended up like this. But when I look at root 3 over 3, you know what I think? I think originally the root was really on the bottom. I unsimplify it. In other words, I look at that root 3 over 3. Let me show you what I do. When I look at that root 3 over 3, I look and I go, you know what? That 3 on the bottom is really 2 root 3s. It's like a little trick, right? Isn't that 3? Mm-hmm. 2 root 3s. And then I go like that in my mind, and I go, oh, that's just 1 root 3 on the bottom, really. Really, there's 1 root 3 on the bottom. And I go, okay, so I need the root 3 thing on the bottom. What's on the bottom? Cosine. So I need to know where cosine's got the root 3. Right there. And I've got it that quick. Do you see that? One more time. We'll practice that. So when I look at the original question was root 3 over 3. But when I look at that 3 down there, I think of 2 root 3s, because that is 3. And then I cancel these guys, and I go, oh, so that's really just 1 over root 3. That's really the root 3 on the bottom is what that really is when you demystify it, when you take out the extra roots and stuff. It's really 1 over root 3. So the root 3 is really on the bottom, and what's on the bottom for tangent? Cosine. So I look for where cosine has the root 3 piece. Do you know what I mean? I start hunting then. I go, where's cosine? Here's cosine sine. There's cosine. He's got a root 3. Cosine sine. He doesn't there. Cosine sine doesn't. I've already got it right here. Cosine's got the root 3 piece with the 2 and the half, and I know those 2's are going to cancel, and that's the thing. All right. So, okay. So here, maybe I'll put it over here. What just happened there? Tangent inverse root 3. Tangent inverse root 3, and I'm a little confused.
Mind-boggling.
Yeah, okay. Yeah, so here's the question. Tangent inverse root 3. So think again, the same kind of thoughts we just thought. What is tangent always? What over what? Sine over cosine. Always want to keep that in mind for a tangent. He's sine over cosine, right? And somehow it's going to be some kind of a combination of a half and a root 3 over 2, right? Mm-hmm. Those two are always getting together one way or the other. So who goes on the top and who goes on the bottom that's going to make that? See what's on the top, what's clear? This is over 1, really. Mm-hmm. So that root 3 is clearly, without any fancy maneuvers, on the top. He's on the top. Mm-hmm. So that means you must have root 3 over 2 on the top, and the half must be on the bottom, and then when the half flips up, see how it'll cancel, and it's all good. See my thinking on that? So that means I'm looking for where the sine is root 3 over 2. And simultaneously, cosine's a half. So look around. Cosine sine, 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 right? I'm just these 2 quadrants for tangent inverse, right? Just those 2. So where is sine root 3 over 2? Right there. And cosine simultaneously a half, pi over 3. Everybody see that? See how Sine is root 3 over 2. We decided sine had to be root 3 over 2 because that's how you're going to get root 3 over 1 is have root 3 over 2 over a half. Right? Let me want to make sure you're clear with that. Root 3 over 2 over a half, right? Over a half. Because if you flip up that half, 2 over 1, cancel. See how it's just going to be root 3 over 1? See how it's right? Say good on that. So the answer is going to be pi over 3. That's the place where that will happen. So again, it's all about, is the root 3 on the top? If so, you're looking for sine root 3 over 2. Or is the last one, the root 3 was really effectively on the bottom, so I was looking for cosine, the bottom of tangent, root 3 over 2, which happens at pi over 6. That's the deal on those. That's how to recognize those. All right, I better move on. They want radians? Yeah, they want. So make sure you're in radian mode. I'm glad to help you. So go ahead. That's different on every calculator. Somehow get yourself in radian mode. And then take the sine inverse, find the sine inverse button. Let me give you the answer. Sine inverse of negative 0.28. I'm getting negative, it's almost the same thing. Negative 0.2837941. I don't know how many places. Nearest hundredth. Oh, so it's going to be negative 0.28, right? Because the hundredth place is right here. Tenths, hundredths. So it's just negative 0.28.
Is it always going to be like that?
No, that one. So you will have to know how to switch between radian and degree mode. All right, so let's try this one on the calculator as well. So you have to enter roots and everything, see if you can do that. Cosine inverse. Radian again, they want radians. So square root 2 divided by 9. So I'm getting 1.41300, and they want two places again, so 1.41. And then tangent inverse, so anyway, that'd be the same. So I'm going to move on from these. So again, if you're having trouble with those, grab me office hours or right after class. Just bring up your calculator. I can help one or two of you. That's great. All right. So on to number 9. Sine inverse of sine of pi over 5. Any thoughts on that? What do you think about it? They're kind of putting them together. Look at that. They're putting a sine inverse and a sine together. Good thinking. Exactly. Does that make sense? That's exactly the right sense of things. Yeah, they're opposites, huh? They're just going to cancel out. This is an easy question. We're hoping for a lot of those on the next exam, right? It's just pi over 5. Does that make... Now, there is a curveball coming, but in general, that's right. That's the right way to think. That's exactly right. They're just opposites. Sine inverse is the inverse of sine. They cancel. Okay, now there is a curveball they can throw at you. This one, tangent inverse, same thing. Boom, 1. Easy question. No curveballs yet. I'll show you the curveball. The curveball, so when you have a function and the inverse, just cancel, boom. Now, the curveball they can throw at you is when the angle is not in the restricted zone. That's the trick. So let me write that out. Is everybody good so far? Let me write that out. So if you have sine inverse of sine of, let's just call it theta, because it's an angle, right? They're just going to cancel, and it's just going to equal theta when, or how about as long as theta is between negative 90 and positive 90, meaning minus pi over 2 and positive pi over 2. Because remember, that's the restricted zone for sine. Remember that special restricted zone we did for sine inverse and tangent inverse? Right? It's got to be in that zone. It has to be in that zone to be true. Well, then what if it's not? Well, then I'll explain that now too. So first off, as long as it's in that zone, boom. Yeah, just cancel them. No problem at all. But if the angle theta is not in the zone, then then what?
Would it be undivided?
There. Then find how far to the nearest x-axis. That's called the reference angle. Remember how we did that a couple weeks ago? Find the reference angle. Find how far it is from the nearest x-axis. Refer to the nearest x-axis. And the answer will be the angle. I'm trying to make this as simple as possible. It's not simple. Because if it's there, yeah, should be negative. Okay. If it's positive, yeah, it's got to be the, okay. So, remember all students take calculus, where the different trig functions are positive. So it's got to be in the same angle. It's got to be in the same quadrant with the same sine value. So in other words, okay, so if the angle is not in the zone, then find out how far, find the reference angle, how far it is from the nearest x-axis. And third quadrant goes, because if you're over here in the third quadrant, think about sine, for example.
That's the second quadrant, right?
Well, that's the second quadrant. Thanks, sorry. Third quadrant, right, starts up here. 1, 2, 3. If you're in the third quadrant, is sine positive or negative? Tangent is positive, so sine is negative. Right, you with me on the, all are positive in the first, sine is positive in the second, the other ones are negative. Tangent is positive in the third. Tangent and cotan, right, is upside down. They always go together. The other four are negative. The fourth quadrant, cosine and his upside down, secant are positive, the other four are negative. Right? So in the third, say you're in the third quadrant. Suppose somebody gives me whatever, some angle, 210 degrees in the third quadrant. Well, is sine positive or negative there?
Negative.
Negative. So now remember, it's going to come back to one of these two quadrants. Because sine inverse always has to come back to one of those two quadrants. They defined it that way. Right? It's got to come back to one of these two. Which one will it come back to? It can't come back to the first because sine is always positive in the first, and we were in a quadrant where sine was negative. So it'll have to go to the fourth. So you see what I'm saying? The third will go to the fourth quadrant. And what if you were in the second? What if you were here in the second quadrant? What is sine in the second quadrant? Positive. So where is it going to go to? Among these two. It's going to go to the first, where sine is also positive. Do you see what I mean by it's going to go back to the quadrant that has the same plus or minus as it does? So that's it. So you find the reference angle, go to the right quadrant, and it's the same reference angle in that new quadrant. So it's quite a bit more tricky when it's out of the zone. It's the same reference angle in that new quadrant. I'll show you one of these. So it's a little complex. So you got to reflect it back into the problem is the restricted zone. We're only allowed to give answers in the first and fourth quadrant. So if we're over here in the second or third, we got to bring it back. That's the deal. That's when it's not in the zone, right? If the angle is in the zone, well then, yeah, boom, they just cancel. It's just theta. No big deal. Tangent. Yeah. All right. So there we go. All right. So as we look at that, we're thinking about tangent now. Remember for tangent goes from here to here, right? From negative 90 to positive 90. That's tangent inverses restricted zone. Is that angle 11 pi over 6 in that zone? Well, sorta. It is, but it's not named correctly. It's, where's 11? Let me get a unit circle up. That'd be more helpful. That's not a unit circle. Okay, where's 11 pi over 6? Right here. Right? Tangent inverse is in this zone. Where's 11 pi over 6? Right here. So it is in the zone, but we don't say it that way. Remember how we say it? We have to say it as a negative angle. We don't say 11 pi over 6. What do we say? What is this same spot? That is the spot. But how do we say it as a negative angle? Negative pi over 6, right? That's 1 pi over 6 down. Right? Because 11 pi over 6, that's 30 degrees down. 180 over 6, right? Pi is 180. 180 divided by 6 is 30. It's negative 30. That's negative a single pi, because that's 1 pi over 6 away from 12 pi over 6, right? So that's the answer. So this answer will be negative pi over 6. Makes sense? That's the same as 11 pi over 6, said in the language they want us to say for tangent inverse. Good? All right. You ready? You making sense out of these? It's a little tricky. It says no calculator, so I'm going to follow, I just do exactly, the test is just like homework. So these will be on the no calculator part of the next exam. The part 1, where you have no calculator. So, all right, so how are we going to find sine of sine inverse of pi? This is super tricky. I'd be very impressed if anybody could nail this one down. I'd be super impressed. One thing to help you start thinking about it is to ask you if this pi right here. Now remember, before I ask this question, pi could be a lot of things. It depends on the context. You might think, well, pi's 180. It could be. Pi's also just 3.14. It's just a number. If we're talking radians, then yeah, it's the same as 180 degrees. But if it's just a number, then it's 3.14. It depends on the setting in which it sits. It depends on the context, doesn't it? So in fact, because pi can fool you so easily, let me just call this W or whatever, whatever, just so it doesn't throw you. They're trying to throw you off by putting pi there. They're trying to make you think a certain thing. Just suppose it was W, whatever. Is that W? And it has nothing to do with W, obviously. It's just, look at where it sits. Look at where it sits. It's sitting next to sine inverse. So what is it? An angle or an answer? What do you put into sine inverse? Remember how we started the lecture today? I said with a toaster, you put in bread, you get out toast. But an inverse toaster, you swap those. So I said a normal trig function like sine, you put in an angle, you get out an answer, like 30 degrees, and the sine of 30 is a half or whatever. But then for inverse sine, you put in an answer and get out an angle. So this is being put into sine inverse. So what is it? An answer. It's an answer, not an angle. That pi is not an angle. Do you see that? Based on where it sits. See, they're trying to trick you. They're trying to give you something that looks like something you've dealt with as an angle before. But in the setting it sits, it can't be an angle. You don't put angles into sine inverse. You put angles into regular sine, or regular cosine, or regular tangent. But into sine inverse, you put answers. This is an answer. Okay, so we got that straight first off. That pi is like 3.14. It's not 180 degrees. It's not an angle at all. It's not an amount of opening at all. It's not an angle. It's being put into sine inverse. Right? So, it's 3.14. Okay, so what? Well, you tell me, can you get an answer out of sine that's 3.14?
No.
How do I know? Think with me for a minute. Let's look at the unit circle. What are the answers? Well, they look weird when there are roots everywhere. How about the graph? We just did the graphing section. Remember sine? When you graph, sine goes like this. What's the highest sine ever goes? The highest answer? 1. I mean, unless you have something in front of it. And negative 1. You're never going to get 3.14. It doesn't go up to 3 up here. 3.1. It doesn't go that high unless you put something in the front of sine, right? An amplitude in front that's other than 1, huh? Sine can't give you that answer that big. You can't get this answer out of sine. Undefined. Try it in your calculator if you want. Hit sine inverse of pi.
It says math
Error. Math error. Depending on your calculator, it'll say something to that effect. Yeah, can't do it. But this will be on the non-calculator part, so you have to just know. So see the trick? They swapped them on you. Let me show you. Maybe that's confusing. They swapped them. See how the sine is on the left now and sine inverse is inside? That's the reverse. Look back here. See how normally they have the inverse on the outside and the regular inside. See right here? Same thing there. Same thing here. Inverse on the outside. See that's an angle there because it's being put into normal sine. See that? That one's an angle because it's being put into normal sine. So you want to be really clear on what the thing's being put into. If I'm putting it into a toaster, it's not toast, it's bread. If it's coming out of a toaster, it's toast, right? So if it's going into regular sine, it's an angle. But if it's going into inverse sine, it's an answer, not an angle. Good on that? We better move on. All right. So now we're in the same section. We're still doing these inverse trig things. This is going to be a big old deal. We're going to draw triangles and back to that whole thing. Why? How do you know? A lot of the battle in math is recognition. Like, how do you know you're supposed to do some kind of big, amazing new thing? Can't we just do what we've been doing? Well, you tell me, look at that for a minute. How is that fundamentally, structurally different than the last 4 or 5 problems we've been doing? They're mixing trig functions, aren't they? It's not sine and sine inverse, or tangent and tangent inverse, right? Look back. See, this was, well, that's the same one. See, this was sine and sine. They didn't go sine and cosine inverse. It was sine with sine inverse, right? Number 12. Look at number tangent, tangent inverse, right? Tangent inverse, tangent. Sine, sine inverse, right? All those were the same trig function, regular and inverse, weren't they? Now, they're mixing them. Tangent and cosine inverse. Different ball game. They're mixing them. We can't just cancel them out in any way, shape, or form. Whether they're in the zone or not in the zone, whatever. We're not even thinking about canceling these out. So everybody see the difference? So how you're going to recognize it on the example. Okay, so what do? You got to draw triangles. So when they mix them, you got to draw triangles. What do I mean draw triangles? We got to like draw a triangle. Remember how we did this before? We made a triangle in a certain quadrant. It's that whole thing again. So here we go. Now,
Can 16 over 20 be reduced?
yeah, we could. We could. Yeah, it's weird they gave me that, huh? Think if there's any problem. Yeah, sure. Let's just reduce it. Good idea. Good idea on that, Kevin. Just make that 4/5, huh? Yeah, because divide by 4 top and bottom. Just make that 4/5. Good observation. So that's not normally doable there, but nice. All right. So tangent to cosine inverse of 4/5. So how do we do it? Well, I'm going to draw a triangle. And how am I going to draw the triangle? Let's think carefully. Well, here, let's just draw a triangle. Which quadrant are we in? Well, we're dealing with cosine inverse. Where is he allowed to be? These two only. Remember, cosine inverse only exists in those two. Remember, if we had sine inverse or tangent inverse, it would only be these two, right? So you always want to keep, whenever you're doing inverse functions, you got to remember the restricted, only 2 quadrants are allowed. Yeah, it comes up all the time with these inverse trig functions. So, now, let me give you a little more explanation about this, which will make this problem easier for you. Basically, if you notice, the sine inverse, tangent inverse, and cosine inverse, they all use the first quadrant, don't they? Right? He's using the first quadrant. They're both using the first quadrant. They all use the first quadrant and then one other quadrant, right? Cosine uses the second. Sine inverse and tangent inverse use the fourth. They all use the first quadrant and one other quadrant. You know why? It's the all students take calculus. Because all the trig functions are positive in the first quadrant. So they all use the first quadrant where they'll put their positive answers. And then they use one other quadrant that'll contain their negative answers. And that's different depending on the trig functions because the all students take calculus, right? All students, so sine is positive here, which makes cosine negative. See, this is cosine's negative zone. That's where he puts his negative answers. Now, well, why didn't the tangent and sine do? Well, sine didn't go here because sine would have been positive there. That would have made two places where he's positive. He doesn't want that. And so anyway, so that's why they went here, because what's positive down here? Cosine's positive down here, right? All students take calculus, right? Cosine's positive down here, which means sine and tangent are negative. So that's where sine and tangent have their negative values. Do you see why they chose those particular quadrants now? So, okay, so with all that in mind, here's what you want to think. When you look at a question like this, and you're saying, okay, cosine inverse of 4/5. That's a positive 4/5 or 16/20. Either way, positive, right? So it's going to be one of these two quadrants. Which one? Where cosine's positive? First quadrant. I know I'm in the first quadrant. So I figured that out. So it's always going to be one of two quadrants when you have an inverse function. And then you just look at the sign. Positive will always be the first quadrant. Negative will be their other quadrant. Whatever that happens to be. In cosine's case, that's the second quadrant. All right. All of that was just to figure out which quadrant we're in. We're in the first quadrant. Because cosine inverse is positive in the first quadrant. All right, so remember how to draw these? You start from the origin, just make a triangle, come to the x-axis. Never over here to the y, huh? Because all the angles started on the x-axis at 0 degrees, so we need to make all of our triangles to the x-axis. Here's our angle theta. Always right there at the origin, like we're used to, right angle here. This is the hypotenuse, as you know. This is the adjacent side. This is the opposite side. All right, cosine. We're talking cosine inverse. What is remember the SOHCAHTOA?
That's adjacent over hypotenuse.
Yeah, SOHCAHTOA. Cosine, that's what we're dealing with, cosine inverse here, is adjacent over, so adjacent must be 4, this side. 5 must be the hypotenuse, huh? Like that. Good there, because cosine is adjacent over hypotenuse. So adjacent over hypotenuse. We good? So now we got to find this other side using the Pythagorean theorem, right? A squared plus b squared is c squared, but that one's so easy. You just know that one? 3. Yeah. How do you know it's 3? Because 3, 4, 5 comes up all the time. And what's the other one? If you just know 3, 4, 5, save you some work. And 5, 12, 13. You should just know cold those two, what are called Pythagorean triples. They use those all the time. They use other things and you'll have to do the work when they use, but they'll use those a bunch and it'll save you some work. If you just look for them. 3, 4, 5, 5, 12, 13. They do those 3 all the time. Now I could have done it formally over here. Let me show you. If it was a harder one, numbers I didn't just know, I would have had to, if I didn't know this was 3, I would have had to say, well, 4 squared plus b squared is 5 squared, right? The hypotenuse is the c, always. And then I would have got 16 plus b squared is 25. Subtract 16, b squared is 9. There it is, root it, 3. Sure enough, it's 3, right? You could have done that easily enough. So it's 3. Okay, so what now? Now we're ready to answer the question. They're asking me for the tangent of the angle. They want the tangent of that angle in the end. So I got all the cosine stuff set up. Now the final answer is tangent of it. So what's tangent? Opposite over adjacent. 3 over 4. Opposite over adjacent. Done. That good? We'll try a bunch of these. These take practice. And like Chanel was pointing out, we'll get to number 19 where they're going to put in X's and stuff too. 17. So we'll build up slowly. Good so far on that one? Other questions on that one? All right, give it a try. So draw your axis system. First find out which quadrant that thing's going to be in. We're talking cosine inverse again. So cosine inverse is always these two quadrants, first and second. One quadrant for his positive values, one quadrant for his negative values. That's how they all are set up. So what's our number? It's positive, so we're in the first quadrant again, aren't we? So first quadrant again. So we'll draw our triangle in the first quadrant. Come down to the x-axis. Put our angle theta right at the origin. So Katoa. So you get cosine's adjacent over hypotenuse. So this is adjacent. Hypotenuse, so this is the adjacent side. The hypotenuse, the opposite. Adjacent is 1. The hypotenuse is 2. Adjacent over hypotenuse. So now we got to find this other side with the Pythagorean, huh? So we go a squared, because any right triangle you can use the Pythagorean. So 1 squared plus b squared is 2 squared. The c is always the hypotenuse, isn't it? So that'd be 1 plus b squared is 4. Subtract 1. B squared is 3. Root it. Square root of 3. So this side is square root of 3. That okay? Now, we're ready to finish the question. Sine is the final thing they want us to do. So how do we do sine? It is opposite over hypotenuse. Sine is opposite over hypotenuse. So opposite over hypotenuse, root 3 over 2. Good. How many got that? How was that? So that's good. Looks like a majority of you. Questions I can answer on that one. We'll do some more with negatives and stuff, but good so far. All right, I'll move off if you're good. Okay. So try that one. So first thing is to draw your axis system and figure out which quadrant you're in. So tangent inverse is these two quadrants, right? Sine inverse and tangent inverse are the right two quadrants, first and fourth. Cosine inverse is the top two, first and second. So, and this up here in the first is where all the functions are positive, and down here is where the tangent will have his negative values. So what do we have? A negative value. So which quadrant are we in? Fourth quadrant. Good? We're for sure in the fourth quadrant. Because tangent has got to be first or fourth. Tangent inverse, that's all he does. And the first quadrant, everything's positive, so the other quadrant, it's negative. We have negative 2/9, we're in the fourth quadrant. So draw your triangle in the fourth quadrant. So I'm going to draw my triangle in the fourth quadrant. Where am I going to go to? Always the x-axis, huh? And you put the angle right at the origin. Always make our triangles that way because the x-axis is where everything started. Okay, and so now SOHCAHTOA. So always our guide here. And we're talking about tangent. So this is opposite, adjacent. So this is the opposite side, the adjacent side, and the hypotenuse. So the opposite adjacent. So this is 2 and this is 9. Right, opposite over adjacent. Now, what about the negative? If you want, you could just skip the negative stuff and just figure it out at the end. Or you could do it now. Either way. And how do you know which one's got the negative? It's simply about right is positive, left is negative, up is positive, down is negative. So, right, 9, that's positive. Down, 2, that's negative. So the negative's on the 2, isn't it? So you could do that, but if you'd rather not worry about that, you could just say, look, in the end, I'm finding cosine. I'm in the fourth quadrant. All students take calculus. All students take calculus. So in the fourth quadrant, cosine's positive. My answer is positive in the end. Forget about sines. That'll work. You know you're in the fourth, and you know cosine's positive. Cosine's the final answer. It's going to be positive. It's got to be positive in the end. So just forget about sines. Just make sure it's positive in the end. You could do that, or you could be careful with the signs along the way, whatever you prefer. Okay, so let's keep going on it. So we got to do the Pythag here, right? Because we got the 2 and the 9. So a squared plus b squared is c squared. The c is actually what I don't know this time. That's the hypotenuse, huh? So 9 squared plus 2 squared, either order. You could switch them. It doesn't matter. 81 plus 4 is c squared. What's that? 85 is c squared. So root of 85. So this side down here, and just didn't finish there, root 85. So this is root 85, the hypotenuse. Good, and then cosine is what I want in the end. Cosine, so Katoa is adjacent over hypotenuse. So adjacent, 9 over hypotenuse, root 85. It is positive, as we already knew it was going to be. But can't leave a root on the bottom, huh? So multiply top and bottom by root 85. You get 9 root 85 over plane 85. Is that good? That's about as hard as they're going to get with numbers. We're going to go to the letters next. But you okay with those number ones? Questions I can answer to that point. They all good? All right. All right. So how about I let you start? I mean, I'll see how far you can get. It's really the same stuff. When I do it, you'll think, well, yeah, that's the same. Let me draw it. We're talking about sine inverse, right? Sine inverse always uses which two quadrants? First and fourth. And the positive stuff is always the first, and the negative values are in the fourth. So, which quadrant do you think it is? First. Why do you think first? Sounds like you guys are uniformly committed to first. Let me question that a little bit. Why? It is? What's x? So we don't know what x is, but we know 3x is positive? Couldn't x be negative 7? So start thinking that way as you're moving up the line in math and science. Remember, variables can vary, can't they? That could be a positive number or a negative. Now, having said that, we really don't know. The actual answer is, I don't know. We don't know. Nobody knows right now what quadrant this is in. Because if x happens to be a positive number, then yes, we're in the first quadrant. If x happens to be a negative number, then we're in the fourth quadrant. The fact is there's no way to know at this point. So I'm just going to draw it in the first quadrant and know that it might not really be there, but it doesn't matter because x is a variable, so it'll eventually tell me what it is. Well, no, it won't. My whole answer will be with a variable. Yeah, so you'll see. Just draw it in the first quadrant. Just draw it in the first quadrant. And take it from there. That'll be fine. We don't really know it's in the first quadrant, but that'll be good enough. We don't know. It's a variable. Oh, does it?
Yeah.
Oh, okay. Nice. I didn't notice that. Thank you. All right, that's helpful. All right, so how do we set this? We're doing SOHCAHTOA, right? SOHCAHTOA. So how am I gonna do this with SOHCAHTOA? Sine is, so this is sine, opposite over hypotenuse. Now, that's for like a fraction. I'm looking at 3x. It's not a fraction. Very good. Good job, guys. Yeah, just put that over 1, huh? Just make it look like a fraction. Then that'll be the opposite and the hypotenuse, huh? Well done. Yeah, just put it over 1. Yeah. So then this would be the opposite. This is the adjacent. And this is the hypotenuse. So it's 3x and it's 1. I'll move that over a little bit. 3x and 1. Oh, wait, hypotenuse. Whoops, I'm doing the wrong thing, huh? 3x and 1. There we go. Yeah. So 3x and 1. Is that good? So, yeah, so if something is not a fraction, just put it over 1, and we can do it that way. Okay. So now find the adjacent. Going to have to do the Pythag thing, right? So we'll do that. It's going to be a little more work than usual, I think, for that. So the a squared plus b squared is c squared. Which one's the c? Yeah, the hypotenuse is the 1, huh? So this will be a squared plus 3x squared. Do you know why I put parentheses around the whole 3x?
Because you're multiplying the whole thing.
The whole
not just
thing.
the x.
Well said. It's the whole b squared. So it'll only be 9x squared, huh? Right, exactly. Good job. And this is just 1. And we're trying to solve for a. Am I going too quick? Making sense so far? So Pythagorean there. A squared plus b squared is c squared. The hypotenuse is the 1. So I'm trying to solve for a, this adjacent side. And so you can just subtract the 9x squared from both sides. So bring it over here. So a squared is 1 minus 9x squared. Like that. And now there's a, what do we do? I got to make it regular a. What do I do to get regular a? Root it, yeah. Root it. Root both sides like that. So a equals, now, I don't know if you know, but you can't actually simplify that. A lot of people think you can. It's a real tricky rule, so that's a lot of what I want to help you with this semester is all those little rules. Yeah, you can't actually, there's a lot, it sure looks like you could just go 1 minus 3x, because the square root of 1 is 1, and the square root of 9x squared is 3x. It's the plus and minus problem. I don't know if I've said much about that or not. Pluses and minuses, I've done the Costco thing. Yeah, so it's that again. Pluses and minuses glue things together, and basically nothing nice can ever be done. And that would be a nice, quick little, you can't do it. If they were times, if that was 1 times 9x squared, totally. That'd be exactly the right thing to do. Just root it. It's all good. It's all right. But with pluses and minuses, you can't do that. What do? Nothing. It just has to stay exactly like that. You can't clean it up at all. It's really good if you just have in the back of your mind in algebra, like that's an algebraic kind of thing, a hard algebraic thing, that anytime pluses and minuses are involved, no shortcuts work. Nothing quick and clean works. It just stays ugly and big. So square root of 1 minus 9x squared, it just has to stay that way. You can see, if you're wondering, like, well, that's weird. Why did math make it that way? It's really just because it's true. Just think about numbers for a minute. Square root of 9 minus 4. That's really not 3 minus 2. It's just not true, is it? Because 3 minus 2 would be 1. And this is really the square root of 5. The square root of 5 is not 1. See how it's just not true? It's just simply not true. Pluses and minuses wreck it. They make things harder. Anyway, so just remember, plus and minuses, you can never do a shortcut. So, okay, so we're good to here so far? Are we good to here so far? We found that other side, kind of complex, square root of 1 minus 9x squared. Has to stay that way. All right, let's answer the final question. Final question is cosine, so kotoa, adjacent, over hypotenuse, adjacent. That square root thing. Over 1, so yeah, it's just that square root thing. There it is. Yeah. Does that make sense how we found that? Well, try it. We can try another one of those with the letters. A little harder with the letters. No questions? Good. All right, if you have any trouble seeing this, these seats are not more expensive. In the future, you can move on up. I just see some people squinting if you're having trouble seeing. Okay. Yeah, let's try that one. Yeah, so I would just, by the way, just put it in the first quadrant. So whenever you have an x, just put it in the first quadrant. Because you don't know what x is, so just put it in the first quadrant. Oh, did they say positive again? Okay, we do know. Yeah, so they're just, that's nice of them. They're giving you that x is positive. So first quadrant. Question?
Can't we just answer that like that?
Can we do what's that?
Can't we just answer it by looking at it?
I know it kind of looks like it, huh? I know what you mean, but it isn't not quite. Like you might think, I don't know what you have in mind, but there's a lot of things one might have in mind. Like you might think, well, look, cotan and tan, they're just upside down of each other. And, tan inverse, can't we do something with that? Actually, not quite. You know what it is? Part of the deal is tangent inverse is not the same as cotan. An inverse function is not the same as a reciprocal function, meaning an inverse function is not just upside down, right? Because that's what cotan is, right? We all know that cotan is upside down of tan, right? That's true. That's not the same thing, though, as saying tan inverse. Tan inverse is not 1 over tan. By the way, it's bad notation on math's part. You probably learned earlier in algebra that like x to the minus 1, doesn't that mean flip x? It does. It totally does. And math comes to this, and then they're suddenly inconsistent. Basically, when you put a -1 power on any function, even f, or g, or tangent, or cosine, or logarithm, or any function, it doesn't mean 1 over. They change their mind all of a sudden. Math is inconsistent here. And instead of being 1 over, reciprocal, it means inverse. Well, what do you mean inverse? Meaning a switching of inputs and outputs, like toaster, toast, bread and toast kind of thing. Yeah, so it's not 1 over. It's inconsistent on math's part. I think if it was up to me, it wasn't up to me, I would have just put an I or something for inverse. But they just use the -1, which normally means flip it. But then when it's on a function, you got to realize it doesn't mean flip it. They change their mind. They're inconsistent. So, yeah. So therefore, no, it kind of looks like you can do stuff that's be quicker and easier like that, but no, they're really just different, even though they're kind of similar. So yeah, got to do it longhand. So let's crank it out. First quadrant, draw our triangle. And SOHCAHTOA as always. And tangent, opposite, adjacent. Here's our angle, theta. Opposite is x. This is the opposite side. This is hypotenuse. This is the adjacent. So what is it? Opposite over adjacent, root 10. So x over root 10, like that, opposite over adjacent. So we do the Pythag work. So let's do the Pythag work. So a squared plus b squared is c squared. So x squared plus root 10 squared is c squared. That's x squared plus 10 is c squared. Getting a little scribbly there. Wait a minute. Did I just do a bad thing? It's just 10, huh? All right, 10 squared. Thanks. Yeah, these cancel. It's just regular 10, isn't it? I was messing up there. We good? A square cancels a root, huh? Kevin?
Can you answer it without doing the Pythagorean theorem? Because
Because here we have the opposite and adjacent. You just flip it.
Because it's just going to be the same answer.
Yeah. Oh, is that what you meant?
Yeah, that's what I meant.
Nice. You meant a good thing. Yeah. You're right. I didn't even notice that. Yeah, why do we have to do all this? Good observation. We know it's yeah. It's just going to be root 10 over x, huh? Absolutely. Done. Great. Good observation. Yeah, because cotan is just upside down. Yeah, I didn't even think about that. I just thought of other things. But they weren't as helpful. That was a better thought. Good. Shall we try one more then? Since that one was so easy, we can do one more now. There we go. All right, so try that one. Again, just put it in the first quadrant. So draw it in the first quadrant. Put our angle theta there. And so SOHCAHTOA So katoa. So sine is what? Sine is opposite over hypotenuse. So this is opposite. This is hypotenuse. So this is the x. This is the opposite side. This is the hypotenuse. This is the adjacent. So opposite over hypotenuse. So square root of x squared plus 9. And we cannot clean up that can't become x plus 3, can it? Because of the plus sign, no shortcuts allowed. Okay, so now we got to find the other side, do the Pythag work here. So we're going to say, okay, a squared plus b squared is c squared. The hypotenuse is the c, the square root one. So square root of x squared plus 9 squared. Yeah, it'll just get rid of the root, won't it? Which is nice. We good to there so far with the Pythag work? A squared plus x squared is that big root squared. Yeah, so the big root squared just cancels, doesn't it? Square and a root just cancel, so we get x squared plus 9. And then what can we do? Yeah. Gonzo. So a squared is 9 rooted. A is 3. That side's just 3. Everybody see that? So I just square rooted it. Square root of 9 is 3. So the adjacent side is 3. So now we're ready to do secant. Yeah, remember that secant is upside down of cosine. So cosine is adjacent over hypotenuse. So then secant will be hypotenuse over adjacent. Upside down to that, right? You with me? The SOHCAHTOA, cosine's adjacent over hypotenuse, so secant upside down, hypotenuse over adjacent. So secant here will be hypotenuse over adjacent. Hypotenuse, the root, square root of x squared plus 9 over adjacent over 3. Bless you. There it is. Making sense? Good. Questions on that? Okay, I want to start the next section, but since we have a moment, I always push off details because of time. But since I have a moment here and then I want to start the new section, let me quickly say I want to give a little more formality to what we're doing so it really makes sense. I'm just going step 1, step 2, step 3. But really, do you see why what we're doing is right? Is because this inside here is that when we write sine, let's just peel that off all by itself. When I write sine inverse of x squared plus 9 like that, remember what that is going to equal is an angle, theta. I don't know what that angle is, but let's just call it theta. Let me be clear, because remember, an inverse trig function, what do you put in? You put in an answer, so that x over root stuff, that's the answer, and it's equal to an angle. Remember when we began today, we said for a regular toaster, you put in bread, get out toast, so inverse toaster, put in toast, get out bread. It reverses inputs, outputs, right? So for a normal trig function, again, you put in an angle like 30 degrees, you get out an answer like a half. So this is an inverse trig function. So this must be the answer. That's what you put into inverse trig functions. And what it equals must be an angle. Okay, so what? Well, what that means is what it equals, what all of this is the same as, is an angle. Some angle. I don't know what angle, but some angle, right? So that's why it's right and true for us to do what we're doing. I just want to make sure I give you the logical foundations for what we're doing and not just say, here it is, step 1, step 2, step 3. That means that whole inside equals is the same as some angle. Right? That's why in the end, it's right to put in, that's why I'm making up an angle whose sine has that answer, right? I'm making up an angle theta, and the sine of that angle has the answer, opposite over hypotenuse, this answer. And then in the end, I'm taking secant of that angle. I just want to show you that's what's happening. That's why that's true. All right. So